We've laid out the groundwork now for explaining the theory of how the sun is supposed to get its energy by fusing together hydrogen. When that process happens, we notice that some things were coming out of the certain steps of the process, like neutrinos were coming out of the process. Those neutrinos are able to fly out of the sun and go flying through the solar system, and they could be flying through you right now. They are going through the Earth, but when they have the opportunity to be captured by something, they can react with other materials as long as they connect with them. Remember, atoms are mostly empty space, and it's easy for those neutrinos to just pass right through. But if you provide denser materials, you do have a chance of grabbing a neutrino and detecting it. But you want to be able to detect it in some way that lets you know, hey, I really got a neutrino there. So, an experiment was done in South Dakota underground to try and detect the neutrinos coming from the sun. We went underground so that we try and screen out extra neutrinos that might be from weaker sources, like from other parts of the universe where there are other stars. So let's just try and detect the ones from our sun by screening out a few other extras. We'll go underground and let the Earth do the screening. So, in the 1970s in South Dakota, they went to a Homestake gold mine under 4,800 feet underground, and they set up this large tank full of a liquid because you'll be able to work with a liquid easier than a solid material when you're trying to detect your neutrinos. And this was filled with 100,000 gallons of perchloroethylene. Notice that in perchloroethylene, you have chlorine in that molecule. Now, when a neutrino hits the nucleus of chlorine, if it can hit a neutron, it can knock a negative charge out of that neutron and leave the neutron then becoming a proton. That would bump the nucleus up to the next element, which would be argon. So a neutrino can change a chlorine atom into an argon atom. That would be a way of counting how many neutrinos you've had come and hit your perchloroethylene. If it turns into argon, remember that's in the column of the periodic table where the elements do not want to combine into molecules with other elements. So argon would no longer be part of this perchloroethylene molecule. It would separate itself out. It would just float around as argon gas in the tank. So, after enough period of time has gone by for this experiment to operate, what you want to do is you want to go and measure how much argon did we end up with in our tank after a period of time. How many neutrinos should have hit the tank in that period of time according to our theory? Let's count up the argon, and that will help us to count up the neutrinos, and we'll be able to see, do we get the right number of neutrinos that we would predict with the theory that says they come out of the sun. And a certain amount of them go spreading into other parts of space, but for the ones that the Earth can intercept, how many neutrinos should we get? Okay, so we knew that number. But when we did this experiment, we only got 1/3 of the expected number of neutrinos from the sun. Uh-oh. Something seems to be wrong here. We did not back up the theory that we had just explained for things coming out of the sun. So, what's going to happen here? Well, when your experiment doesn't go right, you could say, well, I got to do my experiment over again, which is a good thing. But you can also go back and report this to the person who did the theory and say, maybe there's something about your theory you should check. So the person who did the theory, they checked their theory, they went over it, tried to figure out if there was some other way to do the theory. They said, no, this theory's good. We think you should go and check to see how you did your experiment. Maybe there's something you could improve. So they worked on improving the experiment, and it came back with the same result. And so this was science at a standstill. You want experiment and theory to work together, and if they don't, you change your experiments or you change your theory and you try and get things to work together. But these things weren't working together. What were we going to do? Well, one thing that you can do is a different experiment. Do variations on your experiment. So another neutrino observatory was made up in Canada, again underground. They did it differently. Instead of using a chemical, they just used good old water. They surrounded it with lots of photocells so that when neutrinos came in and reacted with the water, they would just make a flash of light. They weren't changing it into other elements. So this actually, since it was not involving a particular reaction in the nucleus, the way the previous experiment did, it wasn't going to be particular about which type of neutrino it would measure. The previous experiment would only work with the electron neutrino. But this one was going to detect all three different flavors of neutrinos. Remember, there are two others, the tau neutrino and the muon neutrino. This one is not going to tell any difference between any of the three types of neutrinos. It'll give you a little flash of light for any kind of neutrino that comes through and hits the water molecules. So when they did that, and they just counted up the total number of neutrino flashes for all three types of neutrinos, they saw that that number for all three neutrinos combined was the correct count of neutrinos that should be coming out of the sun. But wait, the kinds of neutrinos that come out of the sun are only one of the three flavors. Why is it that when you count up all of the three flavors, you get the correct number? That means that they probably are roughly divided into thirds, so 1/3 of them would be electron neutrinos, 1/3 would be tauon, 1/3 would be muon neutrinos. That actually agrees with the previous experiment, which counted only the electron neutrinos and said you're getting 1/3 of what you should. Now that you count in the other two flavors, you add in another 2/3 and get a total number of correct neutrinos. But this isn't what was predicted. We're only supposed to be getting the electron neutrinos coming out of the sun, not the other two flavors. So what's going on? The explanation was that the neutrinos that come out of the sun are electron neutrinos, but as they go traveling across space towards the Earth, they can change flavor spontaneously as they travel. So you can have an electron neutrino come out of the sun, but by the time it gets to the Earth, it's turned itself into a muon neutrino or a tauon neutrino. Is that strange? Well, it would be just as strange if you had your dog at the end of a hallway and you called your dog to come to you, and by the time the dog got to you, it turned into a cat. Yes, that's strange. And so who was going to solve this problem? Right now, the way this turned out was if you said 1/3 of the electron neutrinos have actually been detected and all of the rest of the neutrinos counted up also as the correct number, now the experiment is starting to agree with the theory if you look at it this way. But why do the neutrinos change flavor as they travel? Whose problem is this to solve? The particle physics people had to go and solve this problem. And the only way in which they could solve this problem was to say neutrinos cannot have zero mass. Neutrinos have to have some small amount of mass in order for this to happen. So it was the particle physicists who ended up changing their theories in order to make all of this work. And now we say the theories all agree on what happens in the sun and what happens with neutrinos.